Hello, welcome to the module on our first equation of Maxwell for time-varying case using Faraday's law. In this small presentation come video, you will learn how to derive Maxwell's one of the equation using Faraday's law. As you know, Faraday's law, will reiterate it. In terms of fields, we now say that the time-varying magnetic field produces an electromotive force which may establish a current once suitably closed circuit is found to it. An electromotive force is nothing but a voltage that arises from the conductor moving in a magnetic field or from changing of magnetic fields. And we shall define it as follows analytically. Faraday's law is customary stated as EMF is minus d phi by dt times this match voltages, where phi is a flux linked. Non-zero value of d phi by dt may result from any of the following situations. Case 1. The time changing flux linking a stationary closed path, or it could be relative motion between a steady flux and closed path, or a combination of the two. The minus sign is an indication that the EMF is in such a direction as to produce current whole flux. If added to the original flux, would reduce the magnitude of the EMF. The statement that the induced voltage acts to produce an opposite flux is known as a Lenz's law. It states that the EMF induced is always in an opposite direction of the cause. If the closed path is taken by n term of element, then the Faraday's law can be modified as follows, whereby EMF is n times d phi by dt. Again, the sign is negative, states that it is opposite to the cause of its generation. Needless to say, phi is nothing but a flux passing through one of the n coincident paths. We need to define EMF used in 1 or 2 in general, which is a scalar quantity whose dimension also shows that it is measured in volts. We define the EMF as the circular integral of E dot dl, where dl is a small element through the circular path. So if we integrate E throughout the length, we will find out EMF. So it is worth to note that it is a specific closed path. So when we combine a result from expressions of Faraday's law, you can write EMF, which we have defined as a closed integral along the closed path, and replacing phi with flux density d by dt, b integration of b ds, where the fingers of our right hand inside the direction of the closed path and our thumb indicates the direction of ds. Flux density b in the direction of ds and increasing with time, this produces an average value of E, which is opposite to the positive direction about the closed path. Changing field, now let us consider the case of a changing field within a stationary path. So we first consider a stationary path. The magnetic field is the only time varying quantity on this right hand side of equation number 4. So if it is a time varying, then it goes to the derivative of B. So that is a partial derivative may be taken under the integral sign, and hence we get a final equation as a circular integral of E along the length of the circular path is nothing but a surface integral of dB by dt along the surface. Before we apply the simple results to an example, let us conclude the point form of integral equations. While applying Stokes' theorem to a closed line integral, we can write that the surface integral can be expressed as a curl of a del cross E, where the surface integral may be taken over identical surfaces. The surfaces are perfectly general and may be chosen as differentials. So finally, eliminating both the side surface integral, we can safely write del cross E dot ds is equal to minus dB by dt into ds. So this is nothing but one of the Maxwell's 4 equation, which was the goal to find out. So which is given by del cross E is equal to minus del B by del T.